Here's another exam style question on gravitational potential. Another one including a graph. So we'll have to do some reading off that graph to get some information for questions further down. So it says, the figure below shows the variation of gravitational potential V with distance from the center of the Earth. And the radius of the Earth is 6.4 times 10 to the 6 meters. Okay, so that means at the surface of the Earth there's the potential, and that'll be at 6.4 times 10 to the 6th. Opening question, explain why the V values are negative. Okay, this is a very common question. So we've already talked about many times that the potential at infinity, so very, very far away, is going to be 0. And so as the field does work in bringing you closer to the Earth, you lose gravitational potential energy, so it will be negative values closer than infinity. So just to put that into words, how about the work done per unit mass? Yeah, that's what potential is, work per unit mass. In bringing objects from infinity to a point, okay, the potential at infinity is 0, therefore work has been done by the field, so potential at all points closer than infinity are negative. Okay, so hopefully we've given enough detail there. B, use data from the graph to show that the mass of the Earth is approximately 6 times 10 to the 24 kilograms. Okay, a key equation that links potential and mass. Okay, so there's your gravitational constant, the mass of the planet, the distance from the center of the planet, and that would be the potential at that point. So we're going to use this. So if we rearrange that to find the mass, it's the potential times the distance divided by g. And what we need is we need a v and an r value, which we can get from our graph. As I've said before, try and pick points on the curve where they actually cross key parts of this scale. So don't go between squares, because then you're estimating values, which can then lead to slight errors in your calculation. So let's see, how about there? So if I look, this point kind of neatly crosses quite closely to these lines. And then we need to know, we're going from 0 to 0.5 times 10 to the 8, and it's split up into 10, so that's 0.05 per square, and then that halfway is 0.25, 0.3. So that's 0.3 times 10 to the 8 meters. And then this would be 1 to 2 split in 5, it's going up in 0.2, so 1.2, 1.4 minus 1.4 times 10 to the 7 joules per kilogram. So I'll write those values out. So R was 0.3 times 10 to the 8 meters, and then V was minus 1.4 times 10 to the 7 joules per kilogram. Okay, let's put these values in. So we've got 1.4 times 10 to the 7 multiplied by 0.3 times 10 to the 8. Then we're going to divide all that by g, which is 6.67 times 10 to the 11. And then that comes out as 6.3 times 10 to the 24 kilograms. Okay, approximately 6 times 10 to the 24. Okay, final question. This says, calculate the work done in raising a satellite of mass 2,100 kilograms from the surface of the Earth to a height of 850 kilometers above the surface of the Earth. So we'll draw a little diagram to help us out. So there's the Earth's surface, Earth, and then we're going to move a satellite to some position, and what it's giving us is it's actually giving us the height. So it's not giving us the entire distance r from to the center of the Earth, it's giving us the height above the Earth as 850 kilometers, and then the radius of the Earth that was given to us at the start of the question, 6.4 times 10 to the 6 meters. So the radius of the Earth is 6.4 times 10 to the 6 meters. That means that if you want to know how far from the center, so our R value, we would have to take the radius of the Earth and add the height that the satellite is above the Earth's surface. Okay, so we can actually do that. So if I say 6.4 times 10 to the 6 meters plus 850 kilometers is 0.85 times 10 to the 6 meters. So that comes out as 7.25 times 10 to the 6 meters. Okay, so that's R. Okay, and then what we need to do is we're working out the work done. Okay, and the work done is equal to the mass of the object times the potential difference it's moved from and to. Okay, so we need to know the value of the potential at the surface, I'll call that V1, and then we need to know the value of the potential at V2. And we can always calculate the potential, which is minus Gm over R. So if I want to know the potential at 1, I'm going to have to do R's the radius of the planet, and if I want to know the potential at V2, that R then is the planet's radius plus the height that the satellite is above the Earth. So I will do these down here. Okay, so V1, which is at the surface of the planet, is going to be minus Gm over R1, which is the radius of the planet, and that is minus 6.67 times 10 to the minus 11 multiplied by the Earth's size. I'm just trying to think. I'm going to take the value they give us in the last question, and then we're going to divide that by 6.4 times 10 to the 6, and that is going to come out at about minus 6.3 times 10 to the 7 joules per kilogram. So that's the surface potential. That's the potential, the gravitational potential at the surface of the Earth for having a certain amount of mass and a distance from the centre. V2 then is going to be minus Gm, same constant value, same planet, divided by R, and in this case we mean radius of the planet plus height, so that's 7.25 times 10 to the 6. So the numbers then give us 6.67 times 10 to the minus 11 multiplied by 6 times 10 to the 24 divided by 7.25 times 10 to the 6. And that comes out as minus 5.5 times 10 to the 7 joules per kilogram. Okay, now that we've got these two potentials going from this potential to this potential, we can work out the potential difference. So the potential difference is going to equal V2 minus V1. We went from here, we're going to there. V2 being this value and V1 being this value. So we've got minus 5.5 times 10 to the 7, take away minus 6.3 times 10 to the 7. Okay, these are negative values, so this is actually going to add 6.3 times 10 to the 7. And then that will come out as 7.8 times 10 to the 6. Yeah, it's joules. I was just thinking that value is quite large, but it's a whole magnitude 10 lower. I've done the calculation at the side already so that I don't have to get a calculator out. So that's the potential difference. And then finally, what we're going to do is work done is equal to mass times potential difference. The mass of the satellite was 2,100 kilograms. We're going to multiply that by 7.8 times 10 to the 6 joules per kilogram. So these are going to cancel to give an energy in joules, which is what it's wanting. And that comes out as 1.6 times 10 to the power 10 joules. So that is the amount of work done in raising the satellite to this height above the surface of the Earth.